Part 2, derivatives of base e functions. Okay, at the end of last part, we were left with an equation for the derivative of an exponential function. Okay, it was f prime of b to the x equals b to the x times the limit as h approaches 0 of b to the h minus 1, all divided by h. Okay, because we don't have the skills to factor out the h, we're going to revert back to substituting numbers close to 0 to find our limit. You'll also notice there's another variable in there, so we have to pick a value for b. Now, to set this up properly, I'm going to pick the value 2 and 3 for b, and we're going to figure out both of them. Okay, so we're going to approach 0, so 0, so 0.1, 0.01, 0.001, 0.0001. Okay, so we're getting really close to 0. Now, if I type these things in, okay, so this one has the base 2, this one has the base 3. Okay, so if we just type these into our calculators, look at the numbers that we get. Okay, so it appears the closer we get to 0, okay, 2 to the h minus 1 over h is getting really close to 0.6932, 0.69, okay, yeah. Okay, 3 to the h, as we get close to 0, it looks like it's 1.09 or say 1.1. Okay, from the above, you notice that the derivative of f of x, 2x, okay, so it is 2 to the x times 0.69. The derivative of 3 to the x was 3 to the x times 1.1. Now, here's the really cool part. It stands to reason then that there is some number in between 2 and 3 where the limit of b to the h minus 1 over h equals 1. Right? Below, okay, so 2 was below 1 for that limit. The base of 3 was above 1 for that limit. So it makes sense then that somewhere in between 2 and 3, we're going to have that limit equaling 1. When that happens, this really cool thing happens. The derivative works out to b to the x times 1, which of course is just b to the x. So taking out all that middle stuff, okay, so f prime of b to the x would equal b to the x. At that particular point, the derivative would equal the original function. Now, I kind of gave it away as I put it on the thing, but if you guessed what that special number might be, it's e. So all of that crazy buildup to get f prime of e to the x equals e to the x. It's awesome. That particular function is its own derivative. Very, very cool. All right, so the exponential function f of x equals e to the x therefore has the property that it's its own derivative. The geometrical significance of this is that the slope of the tangent line to the curve y equals e to the x is equal to the y coordinate of the original point. I don't know. I think that's cool, but you guys are probably like, whatever. But yeah, it's all good. Okay, don't forget the chain rule still applies. And therefore, if I have some kind of a u function instead of just x, I have to take the derivative of that u function. Okay, so in ordinary terms, we always have to multiply the original function by the derivative of the u function. In this case, it's always going to be the derivative of the exponent. Okay, so we're going to give those a try with a few examples, and you'll get the hang of it. Okay, so the first one, we start you off with a product rule. Okay, so y prime. So remember, product rule is first times the derivative of the second. Well, the derivative of e to the x is just e to the x. Okay, if we chain rule the x, we just get a 1, so we don't have to worry about that. So first derivative of the second plus second times the derivative of the first. Well, derivative of x squared is just 2x. Okay, awesome. So when we do this, what ends up happening is, look, there's an e to the x in both pieces, and there's also an x in both pieces. So we really should be factoring all those out. Okay, so y prime equals x e to the x, okay, and we take that out, and we're left with, okay, so an x from there, And then we didn't factor out the 2 from there, so it's x plus 2. So there is our final answer. Okay, let's try this one. So y equals e to the sine x. Now remember, the derivative of sine x equals cos x, and the derivative of cos equals negative sine. Okay, that's going to be important coming up. So either way, so the derivative of e to the anything is e to the anything, so e sine x. But now we have to take the chain rule of sine x, so the derivative of sine x is cos x. Okay, so remember that cos x is no longer in the exponent, so I could write it like this, cos x times e to the sine x, just to make sure that you don't get confused. You can leave the cos there at the back. It's really not a big deal. Okay, the next one, so again, it is a product rule. So y prime equals, so first times the derivative of the second. So the derivative of cos is negative sine. So that's negative sine 2x, and oh goodness, I'm going to have to chain rule the 2x part, leaving us with a 2. So that's first derivative of the second, plus, now I'm going to write into D's space here, sorry, it'll be okay. So first derivative of the second plus the second times the derivative of the first. So the derivative of the first is e to the negative 3x, and then chain ruling out a negative 3. Okay, so when we simplify this, I get, oh look, there's an e to the negative 3x in both pieces. Okay, so that can factor out. Okay, and you're left with a negative 2 sine 2x plus, negative 3, which makes that plus a negative, really. So negative 3 cosine of 2x. Okay, and there you have that particular answer. Okay, now, you should have lots of room still, but it seems like I don't, so I'm going to have to add a page here. Okay, and I need to clip that part out. So I'll make that bigger. Okay, sorry guys. See, if I would just write smaller, it would be easier. But that's okay. It'll only take a second. Okay, so I'm going to go back to here, and then we'll paste it. So, clipboard, that guy. Wow. Okay, it is... Okay, so we need to move that and make it smaller. So we don't quite want it that big, do we? Wow, that's really fuzzy. I am so sorry, guys, but that's okay. At least you can see it, and it is still on your page. Sorry, I wasted a bunch of time there, but that's okay. So this one is a quotient rule. That's why we kind of wanted the space. Here, I'll make it smaller. There, now I can actually write on it. Maybe. There we go. There we go. Finally, geez. Okay, so y prime. So quotient rule, you remember, is the bottom times the derivative of the top. Well, the derivative of the top is just negative e to the x, okay, minus the top, so 3 minus e to the x, times the derivative of the bottom. Well, the derivative of the bottom is just e to the 3x, and then we chain rule out a 3. Okay, then all divided by the bottom squared. So e to the 3x squared. Now, don't combine those two exponents just yet, because you'll see something neat. Okay, so if we try and reduce the top, you'll notice that there is a e to the 3x in both pieces. So we have e to the 3x. Okay, and then we're left with a negative e to the x minus 3 times 3 minus e to the x all over e to the 3x squared. So look what happens to the e to the 3x's. That squared cancels off with that. That's really handy. Now, we should be able to simplify something in the middle here. So that negative 3 will distribute into the rest, so you get negative e to the x minus 9 plus 3 e to the x. Okay, so that's e to the 3x. And, oh look, negative e to the x plus 3 e to the x. Hey, that's 2 e to the x minus 9 all over e to the 3x. So a little bit of algebra, but not too bad. And there's our derivative for that. Okay, now I have to go back a page to get to the next part, or the next example. Okay, so number 2, find the equation of the tangent line to that at x equals 1. Okay, so remember, the derivative is the slope of the tangent line. Okay, and then I need the x and the y value. So I could figure out the y value right now. So y at 1 is equal to 1 squared times e to the negative 1. Well, that's just 1 times e to the negative 1, which is e to the negative 1, which is 1 over e. Okay, so our coordinate here is 1, x is 1, and the y coordinate is 1 over e. Okay, you could leave it as e to the negative 1, we just don't typically do that. Okay, if you wanted to though, it's not a big deal. So now we have to find the slope. So the slope is the derivative. Okay, so that is first derivative of the second. Well, derivative of e to the negative x is e to the negative x. And we chain rule, so we take the derivative of negative x. Well, that's just negative 1. Okay, so first times the derivative of the second plus the second times the derivative of the first. Well, the derivative of x squared is just 2x. So there you go. Now, again, you'll notice that if we simplify this, we get x squared times negative e to the negative x plus e to the negative x times 2x. Okay, there's an e to the x in both parts, so you get e to the negative x squared plus 2x. Awesome. Okay, so that looks all right. So that is our slope. So then the slope at x equals 1 is e to the negative 1 times, okay, so 1 squared is 1, so negative 1 plus 2 times 1 is 2. So that looks like our slope at 1, okay, is e to the negative 1 times 1, which is just e to the negative 1, or 1 over e again. Interesting. That's awesome. So now that we have our slope, so remember the equation y minus y1 equals mx minus x1. So y minus 1 over e equals the slope, which is 1 over e, x minus 1. And there you have your equation. Okay, number 3. Find the absolute maximum minimum of the curve y equals x e to the x. State that it is either a max or min using either the first or second derivative test. Okay, so first things first, we have to find our critical values. Now that happens when the first derivative equals 0. So that means we need to figure out our first derivative. Okay, so y prime equals, okay, so x e to the x. So that's a product rule again. So that is first then times the derivative of the second. Well, the derivative of the second, well, derivative of e to the x is just e to the x, plus the second times the derivative of the first. Well, the derivative of x is just 1. Okay, noticing again there is a common factor of e to the x, so we end up with x plus 1. So there is our first derivative. Now, e to the x, this part is always positive, so remember we want the first derivative to equal 0, so that part is always positive, so that doesn't help us out. So really the only 0 we have is when x equals negative 1. So that is the only critical value we have, when x equals negative 1. Okay, so that is going to represent the x value of our maximum or minimum point. So at this point, I'm going to come up here to y equals this, and I'm going to put in x is negative 1. So we get negative 1 e to the negative 1. Okay, when I do that, okay, I get negative e to the negative 1. So that is my y coordinate. Okay, well, that works out to just negative 1 over e. Right, e to the negative 1 is just 1 over e and then the negative. So my potential maximum or minimum is at negative 1 and negative 1 over e. Okay, so that is either going to be a maximum or a minimum. We're just not sure which. Okay, so I'm going to use the first derivative test. So remember, for these kind of questions, okay, we just do a number line and we put in our critical value. So negative 1. Okay, so that separates our number line into 2 regions. Okay, awesome, looks good. Okay, and we want to test on either side of the region. Okay, so negative 2 is over here, that's a good number, and 0 is over here, that is also a good number. So let's just check. Remember, we don't need to find the actual numbers, we just need to figure out whether they are positive or negative. So f prime of negative 2, so that's e to the negative 2 times negative 2 plus 1. Well, e to the negative 2, remember e to the x is never negative, so that's going to be a positive. And then negative 2 plus 1 is negative, so you get a positive times a negative, which is a negative. Okay, awesome, so that guy is a negative. Okay, f prime of 0, so e to the 0 is just 1. And then 0 plus 1 is also 1. So positive 1 times positive 1 is positive 1, which of course is a positive. So that means that this region up here below negative 1 is a negative, or an area of decrease. And the area, or the region above negative 1 is a positive region, or a region of increase. So our point goes down, flat, and up. So that represents, so negative 1 over e is a minimum, or an absolute minimum. An absolute minimum. Okay. At this point, it becomes necessary for me to tell you that there's other exponential functions that we are required to differentiate. However, in order to do that, we have to be able to take the derivatives of logarithmic functions. So you're going to have to wait until the next section to learn those. Thanks. Call me if you need anything about this. Remember, the derivative of e to the x is just e to the x. Okay? Don't forget about the chain rule. Thanks.